Now in this video, we're going to use the integration by parts method again and take a look at several other integrations. And in this case, we're looking at u, the case where u is cosine of x and v is x. So we use uv equals the integration of u dv plus the integration of v du. And in this case, v du is x minus sine of x dx. And that's basically it. It comes down to rearranging the order of the integration and then doing the integral of cosine of x dx, which we know. Now, rewriting it, we have x sine of x dx equals the integration of cosine of x dx, which is sine of x, minus x cosine of x plus c. And again, because this is an indefinite integral, we have to add the constant. And that's it. And now we have another integration. Integration by parts is a very powerful method for finding integrals. Now, this is the same method here, except we're starting out with u equals sine of x and v equals x. And then du is cosine of x dx, and dv is simply dx. And we use the same process. U dv plus v du. Rearranging the sides, we have a new equation. It's not really a new equation, but it's rewriting it into a form that makes sense. And we're going through exactly the same process as we did with the previous integral. except in this case we evaluate the integral of sine x dx. Or the negative sine x dx. And this is our result. It's a pretty quick method. There are other ways of integrating. Sometimes there aren't. Sometimes there's only one way to approach a problem. But sometimes there are other ways of integrating. And we'll see an example of that here. Maybe not in this video. In this next example, I have to take a look at what example we're looking at. Yes, okay. In this example, we're going to look at an alternate way of integrating the secant by just going right to the fundamental forgot the dx, the fundamental definition of what a secant is. And in this case here, we recognize that secant is just 1 over the cosine of x. And if we multiply the numerator and denominator by cosine of x, we can use some trigonometric identities in the denominator. So we have cosine of x over cosine square of x. And now we apply that trigonometric identity, which is cosine squared of x equals 1 minus sine squared of x. Now we use a u substitution where u equals the sine of x and du equals cosine of x dx. And now with our u substitution we have du over 1 minus u squared. And in this particular case, we're going to use a method called partial fractions. Where we break down the fraction 1 over minus u squared into component parts. And we're just going to say a over 1 plus u plus b over 1 minus u equals 1 over 1 minus u squared. And what we do then is solve for a and b. But before we do, we recognize that 1 minus u squared is 1 plus u times 1 minus u. And if we multiply across by that factor, 1 plus u and 1 minus u, we end up with a times 1 plus u plus b times 1 minus u, or 1a times 1 minus u plus b times 1 plus u equals 1, and then setting a value for u, and we end up with b equals 1/2. Now we plug that back into the original equation, and we solve for a. And in this case, you see now I substituted 1/2 for where b was. And in this case, I said u equals 0. And that way I could isolate a. And it turns out that a also equals 1/2. So now I can break down the integral into two parts. I can break it down into du over 1/2 let's see, 1/2 over 1 plus u du, and plus the integral of 1/2. Well, my first integral is 1/2 du over 1 over minus u, and my second integral is 1/2 du over 1 minus u. And now I make another substitution. You can see it's a very lengthy process. It's not a simple process integrating the secant of x dx. And we now use another substitution. I use p as a variable and q because I have the two integrals to resolve. And now we're back down to our familiar form for this integral, which is 1/2 ln p plus 1/2 ln q. And of course, there's a constant that we add to it. Now, all we have to do is go backwards and plug back in those variables that we used for substitution. So we go back to u for, oh, well, first off, we recognize the exponential identity where we have the difference between two logarithms is really the division between them, and then we plug in p and u substitution. So we have the integral of secant x dx equals the natural log of one. Well, we're plugging in here the value for u, which was sine of x. So we have 1 plus sine of x over 1 minus sine of x plus c. But then we use more trigonometric tricks here by multiplying the bottom and top of the argument of the natural log by 1 plus sine x. We end up with 1 plus sine x squared in the numerator and divided by 1 minus sine squared of x plus the constant. And we know that the denominator, here I had some trouble with the screen, we know the denominator is the identity of the cosine squared of x, and the numerator is 1 plus sine of x squared. And using what we know about logarithms, that the factor on the outside, 1/2, is really the exponent for the argument of the ln function. So ultimately, that's where we're going. So here we're just going through the steps. We have 1 plus sine of x squared over cosine squared of x plus c. Now we can apply the exponent, which reduces the numerator into 1 plus sine of x and over cosine of x plus c. And that leaves us with the natural log of the secant of x over the plus the tan of x, tangent of x, plus c. And we've proven now that the integration of the secant of x dx is equal to the natural log of the secant of x plus the tangent of x plus c. But you can see that was quite an involved. You could see that there were many steps and 2 substitutions to get this result, but it was a straightforward integration, albeit a little bit more involved than what we've seen up to now. Now we're going to take a look at more trigonometric integrations. We're going to take a look at the UV method, where U is the secant of x and V is x. Du is then secant of x tan x dx, and dV is simply dx. Sorry about that little. I'm using an iPad with a Hewlett-Packard, so that makes for some strange interaction between the two. So here we use UV equals the integral of U dV plus the integral of V du. Just the typical integral by parts, integration by parts method that we've been using. It's a very powerful method for discovering new integrals. Doing a little rearranging, we have x tan x secant x dx equals x secant x minus the integral of the secant of x dx. And that was the integral that we had just solved in the previous example. So we know what that is. And that's the natural log of secant of x plus tan x. So we have x tan x secant x dx equals x secant of x minus the natural log of secant of x plus tan x, or tangent of x, plus a constant. And that's it. Now, of course, if we were to work this out right from scratch, it would be a very involved integral to solve. But because we had done the one part of it, the integration of the secant of x dx, we were able to solve this particular integration in just 3 lines. Now we're going to look at another aspect of integration called double integration, and setting up the limits of integrals. And this is the preferred method. I know that most math courses teach volumes and areas in different ways, using single integrals, but double integration is really a process that ends up with the same result, double and triple integrals, except you're thinking through the process. I think it's how it should be taught really to begin with, because it's not extremely difficult. It makes more sense in how you think about a problem and how you set it up, because you're looking for the parameters that define the problem. For example, if you have a curve on the xy plane where you have y equals f of x, and you're interested in that integral between 2 points x2 and x1 on the x-axis, and we want to find the area of that curve, or under that curve, between those 2 points on the x-axis. Well, if we think of differential areas, dA, which is equal to dx times dy in rectangular coordinates, and then we basically we're adding up these differential areas between bounded limits, and it's finding these bounds that is the important point. Now here we have dA equals dx dy, and we set up our integral, which sums up these differential areas in the direction, x direction, and in the y direction. And our first integral is going to be dy in the y direction, where y equals 0, or from the x-axis to the curve, y equals f of x. And in the x direction, we are integrating between x1 and x2. So we have the area then equals y equals 0 to f of x, y equals f of x in the first integration, because we're summing up the differential areas in the y direction. And then we sum them up in the x direction. So we solve the integration, the first integration in the y direction. As you can see here, we're evaluating the integral in the y direction. We're going to need a little more room. Get a new page. The area equals the integration between x1 and x2 times f of x dx. F of x is the evaluation of the y value. And then when we integrate f of x, we get g of x, and we just plug in and evaluate that between x2 and x1, and that's the area under the curve is gx2 minus gx1. And that's the solution. That's the general principle. Now let's say we apply it to a square or a rectangle, any kind of a rectangular form. And we define those by discrete limits. So we're going to set up this integration for the area of a rectangle. So here we have our x and y coordinates. we have our y limit, y equals b. So that's our bound. We have x2 and x1. And so that bounded area there in the xy coordinate system is our area. So our limits of integration will be between y equals 0 and y equals b. And we say that the distance between x2 and x1 is equal to a. So x2 minus x1 is a. We set up our differential areas, dA equals dx dy, and we sum them up in the y direction, and then we sum them up in the x direction. So the area is equal to our first and second integrals, y equals 0, the x-axis, to y equals b, dy, and x1 and x2 is our second set of limits in our integrations. So we've evaluated dy, which is evaluated between b and 0, dx, and b is a constant, so I didn't like that, s. b is a constant, so it's not a variable that we integrate. We have b dx, and that is equal to b times x evaluated between x2 and x1, and x2 minus x1 is a, so the area of the rectangle is a equals a times b. So we've proven using double integration that the area of a rectangle is simply the width times the height. Now we're going to take a look at polar coordinates. Oops. Didn't mean to set the screen like that. Sorry about that. Now, in setting up polar coordinates, it's slightly different. We're looking again at a two-dimensional object in the plane, XY plane, and after we clean up this board a little bit, going to show you. Now, we're going to just look at the first quadrant and how to set it up for a circle, because we know that a circle extends through 4 quadrants, but we're just going to look at the first quadrant and set up the problem. And we're going to look at radial coordinates. So we've got a quarter of a circle. Forgive my circle, it's more of a lopsided egg. And our differential area depends on r, and the angle that r makes with the x-axis, dr, the differential area in the radial direction, plus d theta. So our differential area is r dr d theta. r dr d theta. That's our differential area. Now, we say that dA equals r dr d theta, and our radial limit is r, the actual radius of the circle, and we're going to integrate the entire circle, so we're going to go between two angles, theta 1 and theta 2, and between the radius 0 to the radius r of the circle. And so we integrate in the r direction, the radial direction first. So we have 1/2 r squared into evaluated between r and 0 d theta. And that gives us r squared over 2, little r that is, because little r is the radius of the circle, d theta. And d theta in this case is between 0 and 2 pi for a whole circle. So we have small r squared over 2 evaluated between theta equals 2 pi to 0. And that equals 2 pi r squared. So we've proven that the area of a circle is pi r squared. And when you're dealing with things like circles, it's good to use polar coordinates. When you're dealing with ellipses, use elliptical coordinates. When you're using rectangular type objects, integrating, use rectangular coordinates.